you are so passionate, like professors.
Oh, it's
Professors
okay,
are all passionate, and I just introduce my here who are online presenting the papers. Our session chair today, Professor Dr. Muhammad Wahiduজ্জামান, is an accomplished academic and researcher specialist in cloud computing, Internet of IoT, artificial intelligence, and cybersecurity. He is currently an associate professor at Torrens University, Australia, and a visiting researcher fellow at Queensland University of Technology. Previously, he served as a professor at Jahangirnagar University, Bangladesh, and as a research fellow at Queensland University of Technology on an ARC-funded project. Dr. Wahiduজ্জামান holds an MSc in Telecommunication and Computer Networking Engineering from the UK and a PhD in Mobile Cloud Computing. He has published over 100 research papers and received Elsevier Best Paper Award in Paris and accumulated nearly 4,000 citations with an age index 28. So Professor Wahid has joined as a session chair, please. And here is Professor Sajjad and Professor Kanat Rai. Kanat Rai, you see? So let's our presenter. Are you listening to us, presenter? All presenters are here. All presenters are here. Yes. Huh? I will give the chair. Many presentators here. Okay, I will just moderate, and please, up to you, Professor Wahiduজ্জামান, please.
all right. Yeah, am I audible?
Yes, you are audible. You are audible.
All right, thank you, and welcome everyone for this sessions for the 5th International Conference on Trends in Electronics and Health Informatics 2025. So this session is for titled as Deep Learning and Medical Image Analysis. So let's start the session. So I would like to invite the first presenter, and the title should be from the PID 2025322, Tomato Leaf Disease Detection using a hybrid efficient net B7 model. Should be presented by Abdullah Noman, Muhammad Tamim Hossain, MD Alamgir Hossain, MD Nahid Hassan, Bishwajit Ghosh, and Jahanur Bishwas. Yes, please present your presentation.
Hello, good afternoon, everyone.
Good afternoon. It is audible. Very good. We can hear you.
Sir, I am Abdullah Noman from Department of Computer Science and Engineering at Dhaka International University.
Very good. Thank you. And we are a little bit late. Sorry for the presenters.
Okay, sir. Basically, today I will present our deep learning based tomato leaf disease detection using an efficient net B7. And this is the joint work with my co-authors Muhammad Tamim Hussain, MD Alamgir Hussain, MD Nahid Hussain, Bishwajit Ghosh, and our respected supervisor MD Jahanur Bishwas. This is the table of content. Basically, here is the first roadmap. First, the background and motivation, then our research goal and contribution, then the methodology, research gap, dataset and implementation, then results and discussion, ethics, conclusion, and future work. Now I am describe about background and motivation of our work. We know tomato is among the most widely produced vegetable crops globally and a cornerstone for both nutrition and rural economies. Unfortunately, tomato faces over 200 pathogens fungi, bacteria, and viruses, causing 20 to 40% yield losses worldwide, amounting to roughly 220 billion annually. Traditionally, traditional visual scouting by expert is slow and error prone. So there's strong motivation for automated AI-based diagnosis from images. Recent advances in computer vision and deep learning make this feasible. CNN-based system can learn discriminative features directly from images and have outperformed classic handcrafted pipelines in this domain. Then I am describing about our research goal and contribution. Basically, our goal was to build a robust, accurate, and reproducible pipeline to identify 10 tomato leaf diseases, where 9 are disease class and 1 is healthy class from our image. Our key contribution are a hybrid CNN built on efficient net B7 with multi-scale fission, extraction, and Fisher pyramid-like fission, a full training pipeline, pre-processing, balanced augmentation, and class weighting, early stopping, and checkpointing. Then number third, state of the art performance on a public data set, 99.50% our test accuracy and 99.10% our validation accuracy, outperforming custom CNN, VZ16, and DenseNet 1-to-1 baselines. Now I am describing about our dataset and implementation. We used a public dataset from Kaggle, and the number of data was 11,000 annotated images and 10 classes. Then we split this data in 70% for training, 20% for validation, and 10% for testing. Then we used now I'm describing about dataset. I am saying tomato leaf disease dataset from Kaggle with 10 level categories, and then we work on augmentation and to improve generalization and addresses class variability. We applied rotation, shear, zoom, horizontal flip, and brightness shifts via image generator. This produce diverse views and reduce overfitting. And this figure 3 and this figure 3 is described of our augmentation for 10 classes, and this is our proposed architecture. Here we take dataset, then we split test, training, validation, and test. Then we evaluate model. We use here 4 model: custom CNN, DenseNet, VGG16, and hybrid efficient net B7. Then we choose our best model, which was hybrid efficient net B7. Sorry. Now I am describing about our methodology, which model implemented. I already said we used custom CNN, basic architecture with 3 convolutional layers, fine-tuned VG16, remove top layers and fine-tuned last 4, fine-tuned dense net, then hybrid efficient net B7 integrated multi-scale Fisher fusion from intermediate layers, block 3 added, block 5D, then block 7D combined with refined linear unit, then base normalization and dropout layer, which was 0.5. Now I am describing the results and discussion section. The performance comparison was the model name are custom CNN VG16, fine-tuned dense net 121, hybrid efficient net B7. The test accuracy is 62.77%, 7.77% was custom CNN, then 85.74 was VG16, and fine-tuned dense net 1-to-1 was 93.75%. And our proposed methodology, which is best hybrid efficient net B7, was 99.50%. And this was the precision, recall, and F1 score. This is the performance comparison where comparing our proposed system with existing works. This is the existing work, and this is the validation accuracy of others' work, and this is our proposed work, which was 99.10% accuracy. They use Linet CNN, AlexNet, SqueezeNet, Custom CNN, and DWT GLCM VZ16. We use a hybrid efficient net B7. Due to less time, I want to describe only our best proposed model. This is our best proposed model confusion matrix. This confusion matrix tell the story visually. The hybrid efficient net B7 model correctly classifies all test sample across all classes, eliminating the confusion we see in the other three models. And this is the accuracy and loss curves of our efficient net B7. Learning curves show fast convergence and minimal overfitting for the hybrid model, and training accuracy approaches 0.997 and validation accuracy was approximate 0.991, and the corresponding losses drop near zero, which we see in the figure. Then I am describing about ROC curve. This is the ROC curve of hybrid efficient net B7. It is on multi-class ROC. All classes achieve AC equal to 1.00, indicating excellent separability and robust sensitivity and specificity. This is our model comparison of all model. Here we show training accuracy, validation, then test accuracy. It is for custom CNN. It's for VZ16, DenseNet 121. Then it's the best, and it is the hybrid efficient net B7. Now I'm describing about ethics, conclusion, and future work. Basically, ethics, the study was publicly available dataset, and no private data or human animal subject were involved. And the conclusion is, to conclude, our hybrid efficient net B7 with multi-scale fission forms a strong and generalizable classifier for tomato leaf disease, delivering 99.50% test accuracy and 99.10% validation accuracy on a public dataset and outperforming widely used baseline. And our feature works are validated on larger and more varied real-world dataset, harden the model to field condition, and compress the model for on-device decision support tools for our farmers. Thanks for listening. I am happy to take your question.
Thank you, Noman, for your nice presentations.
Welcome, sir.
Yeah, does anyone have any question for Noman?
Anyone having question? If not, a session chair can ask question, please.
Yeah, just I have one. It's not very technical. Just one thing that Noman, do you know that which country or which region in the world they produce the most tomato in the world? Is there anything like that? Do you know that?
I know India, Italy, Bangladesh, etc.
Yeah, they're the most tomato producing countries in the world.
Yes, sir.
Yeah. All right. Thank you. Thanks, Noman. Thanks for your presentation.
So, are you undergraduate student, Noman? Undergraduate student, Noman?
Yes, sir. I am currently in CSC final year.
Oh, fantastic, fantastic. Very good, very good.
Thank you, sir.
Farooq Ahmad want to be second because he has.
Sir, can I leave?
Yeah, you can.
Okay, please. Professor Wahidur Jaman, can we call project ID 2025280? He has a request.
Sure. Yeah, sure. I'm
he
doing
has
that.
an exam. Yeah, please.
All right.
Please.
All right. So I'm just a little bit changing my order due to one request has been made by one student due to exam. So I'm considering the PID 2025280. The paper title is RVE, an optimized ensemble model for breast cancer detection, presented by Jalal Ahmed, Farooq Ahmed, MD, Alamgir Kabir, Abu Zahid, MD, Zulhasuddin, and Tawhid Bhuiya. Please welcome them and please start your presentation. Thank you.
Yes, sir, I'm here, Farooq Ahmed from paper ID 2025280. Hello, everyone. Here I am presenting the paper titled RVE, an optimized ensemble model for breast cancer detection. And here with me, my co-authors, Jalal Ahmed, MD, Alamgir Kabir, Abu Jahid, MD, Jalaluddin, and Tawhid Bhuiya. So at first, there's the outlines, like I will first talk about the introduction, problem statement with the research objectives, and also the methodologies and my results sections.
Can you make
So,
it?
at first,
Can you make your presentation in presentation mode, please?
oh, okay.
Thank you.
Is it okay, sir, right now? Okay.
Yeah, it's fine. It's fine.
Well, breast cancer, all of us know that amongst all the cancers in the world, the breast cancer is the major global health threat because it is really enhancing, or it is really increasing the death rate of the women across the world. So there are millions of women that are diagnosed with breast cancer, but due to the early detection, it's not possible. There are really not much available things for saving their lives. But one thing is the primary screening method. That is mammograms, but it already faces some kind of challenges due to the breast density and also the observer's variability. But deep learning in this case can help to empower the automated diagnosis, like computer-aided diagnosis, for accurately and early detection for the breast cancer and reduce the human error. So the existing models that are really available in the literature that are really sensitive to extreme prediction and sometimes causing the unstable results. And moreover, the probability averaging ensemble also amplifies some kinds of outlier also. But here in our work, we propose a rank-based ensemble that really amplifies the models together and to stabilize the prediction from a rank-based fusion for a balanced and accurate prediction. So in the literature, there are some literature that can that have already achieved a very good accuracy of 94 to 96%, but they always lack of robustness and consistency. Some transfer learning also improve the results by using some small data sets, but yet they are not remain so they have some problems. Like the transfer learning improved in small data sets cannot handle the extreme prediction and also remain problematic. But in our model, as we have used a rank-based fusion, that is really stable for the predictions. So here you can see that some literature or some authors have done some works, but they have some limitations like the probability averaging, and also sometimes they are causing the sensitivity too extreme. And Sahu et al., who lack the systematic statistical validation, and also the trade-off between the precision and recall is unbalanced in his literature. And another thing is that Liu also used an attention-based mechanism, but it has a really heavy computational complexity and also need a large memory for that. So in our work, we are trying to find out the research questions like that. How can a rank-based fusion model can improve the stability and accuracy of an ensemble model? And another thing is that is our model can outperform the traditional CNNs? And also, are the observed improvements are statistically significant? So we want to see that our result is statistically significant or not. So the main objective is that to develop a rank-based ensemble that combines the VGG inception and ResNet model together, and that can that are compared with the existing CNNs models and transfer learning. And after that, finally, we have validated our model by statistical tests. So the main outcome is that we have achieved a 96% of accuracy with a balanced sensitivity and specificity. And another thing is that the reduced false positive and negative rates is really reliable for the clinical interpretation. And we have also shown a really good potential for the integration of this model in the diagnosis system. So here's the main methodology of us that we have collected the RSNA dataset from Kaggle with 8,013 images of mammogram. And after that, we have done some kinds of pre-processing and also the augmentations like flipping, rotation, scaling, sharing to enhance the data and also for the generalization. And the training is made with a 5-fold cross-validation to ensure the stability of our model. So here's the main proposed methodology of ours that our RVE integrates BGG19, Inception V3, and ResNet 152 version 2 networks through a rank-based ensemble, in which at first all the base models are ranked into their probabilities. They also calculate the rank of the probabilities, and then also it calculate the fuse score. And after the calculating of the fuse score of all the classes, it really combines all the prediction of the 3 models and provide a result that enhance the ensemble stability. And the fusion mechanism really significantly reduces the misclassification rate that achieve a better precision across both the cancer classes and also for the non-cancer classes. And the results is like that we have got a good precision and recall, and that are good for both the classes. The precision is for cancer classes, the precision is outperform for the non-cancer classes, and the overall accuracy of our model is 96%. That is really good in terms of the RSNA dataset. And we have also compared our model with the 13 baseline models and also with another ensemble, weighted ensemble model. And we got that our rank-based ensemble model has outperformed all of these, like the weighted VIR ensemble got an 84% of 8% of accuracy. And the other baseline model also got the accuracy below our proposed model. And after that, we have also conducted a statistical test, like the Friedman test and also the NAMI test. The Friedman test is really because we want to see that there is the difference between the models. And the NAMI test is like we have used this because we want to see if there is any kind of difference, which model causing the difference between all the models. So in terms of ours, we have seen that our RV obtained a rank of 1%, 100%. So that means that our model is statistically outperforming all the baseline models. And already we have discussed that the other models that are used in the literature, they also lack robustness and also the stability, and also doesn't have the clinical reliability. So we have tried to encompass all the things and also try to mitigate the limitation in our study by attaining a good accuracy in terms of the RSNA dataset and also with the statistical validation. So in future, the researcher might also can have a multiple data set, and they can also do some kinds of explainable AI here for the trustworthiness and also for the interpretability. And also this framework can be used by the other researchers to do the further research in the clinical intervention and also others. So these are the references. We want to also thank Daffodil International University for helping us, and also the Washington University of Science and Technology, and all the co-authors of mine and the reviewers. Thank you, sir. I'm available for the question and answer session.
Thank you, Farooq Ahmed, for your nice presentation. So
thank you, sir.
Yeah. So does anyone have any question for Farooq Ahmed?
Yeah, question. Any question? Okay, so just I have one query. What is the data size? What was the sample you have taken?
The data size is, sir, we have collected it from Kaggle, and the data set was there are 8,013 images.
Okay, so how much, what is the percentage you have used for training?
Sir, for training, we have used 70% of data set.
70% of this. And regarding this robustness of this, model, when you have these results and all this, have you checked it with or compared it with the other models, the robustness and stability of this model?
Yes, sir. We have checked our model with the existing literature, and in the existing literature, we have compared with 5 to 6 literature, and most of them has got an accuracy of 95% to 95.8%. So by checking that, we call that our performance is really good and superior to other models.
So, because, whether you have any chart of that, about this particularly, how much,
Oh, sorry, sir. We
robustness.
haven't included the chart in the presentation
Okay,
slide,
okay,
but
okay.
it is available in the paper.
But you have already done, huh? You have done and compared that, Okay, fine.
Yes, sir.
Fine.
Okay.
Okay.
Thank you for, I think you also explain why you use RV several times in your conclusion and in your beginning as well. So
Yes.
yeah, and you also mentioned the Kaggle data set. Yeah, that's I found. So that's good. Thank you.
Thank you, sir.
Yeah. Thank you very much, Farooq. So we can move into the other participant. So now I'm inviting the PID 2025327 deep CNN based ECG classification for heart disease diagnosis with grade CAM driven interpretability. It should be presented by Shihab Shahriar, MD Junaid Haq Bhuiya, Jahanur Vishwas, MD Nahid Hassan. Please go for your presentation.
Assalamu alaikum everyone and good note. Am I audible?
Yes.
Sure. Screen. Is my screen visible to you?
Yes, Shihab.
I am Shahriar and it's an honor to present our research titled Deep CNN-based ECG classification for heart disease diagnosis with GradCam-driven interpretability. This work was carried out under the guidance of my co-authors Jahanur Vishwas, Nahid Hassan, and MD Junaid Haq Bhuiya. Our focus on using deep learning for automated heart disease diagnosis from ECG images while also ensuring interpretability and clinical relevance. Nowadays, heart disease remains one of the leading causes of death globally. Early diagnosis can significantly improve survival rates. Traditional ECG interpretation, however, depends heavily on expert cardiologists, and it's both time-consuming and subjective. In recent years, deep learning, particularly convolutional neural networks, has shown remarkable potential to analyze medical images. Our motivation was to leverage CNNs for automated ECG classification, making this process both efficient and trustworthy. This study was designed with 5 main objectives: to classify ECG images into 4 categories as atrial heart block, hypertrophic myocardial infarction, and healthy ECG signals. To evaluate and compare the performance of 5 CNN architectures as ResNet 50, VGG 16, Inception V3 Exception, and Inception ResNet V2. To identify the model providing highest accuracy and reliability, to integrate GradCam to make the classification decisions visually interpretable, and finally to compare our findings with existing studies in the same field. Several studies inspired us and guided this work. For example, the paper Hanun et 2019 showed of CNNs in detecting arrhythmias from ECG signals. Later work such as the paper in 2022 used a hybrid CNN LSTM based framework. They achieved 98.24% accuracy for arrhythmia detections. And other papers was also discussed about multiple CNN-based models. Those references are given in our paper and explained briefly. No study combined 2D ECG images analysis as our paper does. This slide was for the dataset explainability. Especially the dataset was used in this study. Heart disease prediction image was collected from Kaggle. It contained almost five five classes, but we dropped one of them. That was for COVID-19 because we saw some unavailability and data corruption on that classes, and we filter out these four classes. The dataset was divided into training, validation, and testing sets. All the image was resized to 224 times 224 pixels for compatibility with our pre-trained CNN architectures. We didn't implement any type of data augmentation to benchmark our model's pure performance. If we move to the data processing pipeline, we began with data pre-processing with normalization and resizing. Then we applied transfer learning using several pre-trained architecture. As I mentioned earlier, these five architectures was fine-tuned on our ECG dataset. The training used categorical cross-entropy loss and Adam optimizer with early stopping to prevent overfitting issues. Finally, at the end, we select our best model and applied GradCam, which was identifying the medical relevance and focusing on that section where our model is targeting. Our selective model was discussed briefly on the paper. As VGG16, it was a classic model known for simplicity with a high number of parameters. Inception V3 captures multiple features using parallel convolutions. Exception was an improved version using depthwise separable convolutions. Inception Resonate V2 merges Inception modules with residual learning. And finally, our most accepted CNN architecture Resonate 50, which uses escape connection to eliminate vanishing gradient problem and enables deeper, more accurate network. Among all, Resonate 50 proved to be the best, most robust, and consistent in classification accuracy. We put the best performed CNN architecture in this slide, and also we discussed briefly in our paper. The Resonate's GradCam image is shown here, visually verified that the model attention aligned with key ECG waveforms region such as P wave, T wave, and QRS complex, enhancing the trust and interpretability. The GradCam visualizations validate the network focus on physiologically relevant waveform regions. Although the dataset was modest in size, the model generalized effectively due to careful fine-tuning. However, challenges remain such as data expansion, clinical validation, and ensuring real-time deployment feasibilities. Addressing this will make AI-driven ECG interpretation even more robust. This is our model comparison table and the radar chart for all five CNN architecture we have used. If we carefully see the model comparison table, we can see the Resonate 50 outperform all over the model with the highest accuracy. The radar chart also visibly shows that. This was our Resonate 50's AUC curve and rock curve image and the confusion matrix image. The confusion matrix shows that the Resonate 50 achieved most perfect classification across all four classes. The rock curve indicates the AUC values near 1.0, confirming excellent sensitivity. And the previous on the previous slide, the image of GradCam we visualized which ECG segments influence the most predictions and highlighted regions corresponded closely to actual complex waveform and peaks. This was our overall result for ResNet 50, which achieved 99.75% test accuracy and balanced F1 score. This was the comparison with the existing work. Here are some anomalies like our model, no, our structure was not directly comparable one-to-one. We just aims to contextual performance over the existing works because we have a different data set and we cannot access the data set they have used on their studies. To conclude, our proposed ResNet 50 based ECG classification framework achieved outstanding result, as I mentioned, 99.75% test accuracy with clear and interpretable predictions. The integration of webcam and GradCam made it possible to visualize decision regions, bridging the gap between AI and human reasoning. In future, we aim to expand the dataset with real-world hospital ECGs, applying data augmentation, and possibly GAN-based synthetic ECG generation. Conclude, conduct clinical validation to explore real-time development and healthcare settings. Ultimately, the goal is to support faster and more reliable cardiac disease diagnosis using trustworthy AI systems. These are some references throughout this research. Several existing works and authors played a guiding role. I have drawn insights among these studies, which helped and shaped both the methodological and analytical directions of this study. The research journey was both challenging and deeply rewarding as it connected theoretical understanding with practical innovation in healthcare AI. I would like to express my heartfelt thanks to my co-authors, mentors, and my university, especially Dhaka International University, and the reviewers for their valuable feedback and encouragement through this research. At the end, thank you for your attention. If you have any queries, it will be much pleasure for me.
Please.
Yeah. Thank you, Shihab. Thanks you for your excellent presentation. So does anyone have any question for Shihab?
Okay, I have some queries. Basically, this when you consider this deep CNN, there are certain, there are some black box. Okay, so certain, problem with this, this kind of, there is no transparency. So how do you see, problem here? How do you overcome that? Because they are basically, they are opaque, and you are lacking the transparency in dealing with this model. Because there are some class imbalance problem and sensitivity problem in this type of problems. So did you encounter that, or did you take measure of that? This is my first question.
Sir, we use this model as pre-trained that our dataset has a limited size, like almost 4,000 images, and we also mentioned that we didn't implemented any types of augmentation to keep our model remain original prediction. So we didn't apply any special method to handle class imbalance, and we splitted the dataset equally rather, but we didn't implement anything for class imbalance dealing. And for the acceptability, we used the GradCam visualization. It is a method which can show the targeted region for the model's prediction over the images. I hope this is almost enough to believe in the model's prediction.
Okay, so regarding the GradCam one, so that is also, there is some layer dependence, because the convolutional layer, that one, you are using which layer you are using, that may affect the result or the interpretation. So is there any, have you taken taken any measure of that, or did you encounter any problem for this, which particular layer you are taking into account?
No, sir, we didn't encounter any type of problem.
Okay. Okay, because sometimes it is dependent on some layer. Some layer dependent is there. Okay. Okay. Good presentation.
All right, Shihab. It's not a question.
Thank you.
I have an observation. In your slide 3 and in your slide 11, where you talked about other papers, your slide 3, next one, yeah.
Sir,
I can see your latest article is published in 2022, but still you have 2023, 24. We haven't got any updated paper. So what's the reason? I mean, is that have you you are not
sir,
able to
we
get the
searched,
right paper, or
we
not
searched
really
for similar works in Google Scholar,
right.
but we didn't find any types of paper that aligns with our works. So at the latest paper we got 2022, with some kind aligned with our work. So we took that, not the latest paper after that.
All right, yeah, that's one question from me. This is observation. So if you have anything that you can go and you can search for 2023-24 recent published paper, there is so you can update your things.
Sure, sir.
Anyway, yeah, thank you. Thanks for your presentation, Shia. Thanks.
Thank you, sir.
Now, I would like to invite the paper PID 2025335, Self-Supervised Learning for Diabetic Foot Ulcer Classification by Tanzim Mahmood. Please.
Hello, I'm here to present on behalf of my co-authors. May I start?
Yeah, sure, proceed.
I think there is a mistake. The authors are all not there. So sorry, and it's late. So thank you, please.
Is my screen visible to all of you?
Yes, yes.
Yeah. At first, my warm greetings to the respected chairs, coordinators, and moderators, and also my fellow researchers. I am Purnima Miyaji from the University of Chittagong, Bangladesh. And it's my great honor to present our work, Self-Supervised Learning for Diabetic Foot Ulcer Classification at this conference. Our research addresses a critical challenge in medical AI by reducing its dependency on expensively labeled data. This presentation will be starting with introduction and then problem statement, objective, and so on. Let me begin by highlighting the significance of our research focus. Diabetic foot ulcers, commonly known as DFUs, represent one of the most severe compilations of diabetic mellitus. To put this in perspective, according to the International Diabetes Federation, over 537 million adults worldwide are living with diabetes today. And alarmingly, approximately 15% of them will develop DFUs during their lifetime. As you can see from this clinical progression chart, what begins as a superficial ulcer can rapidly deteriorate to deep ulcers, to bone infections, and eventually partial or complete foot gangrene. The clinical reality is stark. Without early detection and intervention, DFUs frequently lead to hospitalized and, in worst cases, amputation. The conventional approach to automating DFU detection uses superficial deep learning, which demands extensive datasets with expert annotations. However, in medical domains, obtaining these levels is exceptionally challenging. It's time-consuming, expensive, and requires scarce clinical expertise. This creates a significant barrier to developing accessible AI diagnostic tools, particularly in resource-limited settings. This brings me to our core problem statement. While the medical need for early DFO detection is undeniable and urgent, the current AI development paradigm faces what we call the labeled data bottleneck. Let me break this down. First, there's a clinical medical need. DFUs are severe, widespread, and early detection can literally save limbs. Second, the AI challenge, state-of-the-art supervised learning requires massive level datasets that are impractical to obtain at scale. And third, the core problem. This bottleneck prevents us from building scalable and accessible diagnostic tools that could benefit millions of patients worldwide. The fundamental question driving our research was, can we develop AI systems that can learn effectively from medical images without requiring extensive manual leveling? And to answer this question, we established 4 clear research objectives. First, we aimed to implement and adapt a self-supervised learning framework specifically for DFU images. Second, we sought to rigorously evaluate the quality of self-supervised learned features through this label-free approach. And third, we designed to experiment to benchmark SSL performance against traditional supervised learning. And finally, we aim to demonstrate the practical viability of SSL for real-world medical image analysis where level data is scarce. Essentially, we wanted to create a pathway for developing accurate diagnostic tools without the prohibitive cost of data annotation. For our experiments, we used the publicly available diabetic foot ulcer dataset. This dataset originated from the Diabetes Center of Nasiriyah Hospital in Iraq and was collected with proper ethical approvals and patient consents. The dataset contained 493 original full foot images, but for our classification task, we worked with the preprocessed patches, where 543 patches of normal healthy skin and 512 patches of abnormal ulcerated skin. Each patch was standardized to 224 by 224 pixels, which is compatible with standard CNN architectures like ResNet 18. Notably, these images were captured under varying clinical conditions, different lighting angles and devices, which actually helped our model to learn robust features that generalize across real-world variations. Now, let me walk you through our two-phase methodology. In phase 1, we performed self-supervised pre-training using the Sinclair framework. And the benefit of this approach is that it learns entirely from unlabeled data. Here how it works. We take each unlabeled DFO images and create 2 randomly augmented views. Think of them as different perspectives of the same image. And these augmentations include random cropping, color jittering, and Gaussian blur, and other transformations as well. Both views pass through a shared ResNet 18 encoder, followed by a projection maps that maps the features to a lower dimensional space. And with the antecedent cross entropy loss function, it trains the model to recognize that these 2 different looking views actually belong to the same original image while ensuring they are distinct from all other images in the batch. Through this process, the model learns meaningful visual representation without ever seeing a single layer. And in phase 2, we move to downstream classification. We remove the projection head used in pre-training and freeze the now knowledgeable encoder. We then use it as a fixed feature extractor. On top of this feature, we train simple classifiers, a support vector machine, and a multilayer perceptor to perform the final ulcer versus healthy skin classification. For comparison, we also trained a standard supervised ResNet 18 model end-to-end on the level data, which represents the traditional approach and our performance upper bound. Third, in this slide, the methodology architecture diagram visually summarizes our entire approach. You can see from these three parallel streams. The first one, the supervised baseline, in the center, our core self-supervised pre-training phase, and last, the downstream classification phase. Notice that how the self-supervised pathway takes raw DFU images and through augmentation and then projection, while the supervised pathway goes directly from the labeled images to the classification. The visual contrast highlights the fundamental differences in how these approaches learn. Now to the results that validate our approach. When we used a linear SBM on our SSL learn features, we achieved remarkable performance like 95% accuracy with perfectly balanced precision, recall, and F1 scores. The confusion matrix for SimClear and SBM shows excellent class separation with minimal misclassifications. However, when I used MLP classifier on the same features, performance dropped to 86% accuracy with some imbalance between precision and recall across classes. The interesting findings suggest that our SSL learn features are particularly well suited for linear separation. Now, looking at our supervised ResNet 18 baseline, it achieved 97% accuracy with near perfect metrics. Most impressively, it demonstrated 99% recall for ulcer cases, meaning it missed very few actual ulcers. It is crucial for clinical applications where false negatives can have serious consequences. This comparison table tells a compelling story. While supervised learning remains the performance and gold standard at 97% accuracy, our SSL approach with SBAM comes remarkably close at 95% accuracy. Consider what this means. We achieved within just 2 percentage points of supervised performance, but without using any levels during features learning. This represents a massive reduction in annotation cost and effort for only a minimal performance trade-off. For healthcare systems with limited resources, this could make the difference between having no AI diagnostic support and having a highly effective screening tool. In conclusion, we have successfully demonstrated the self-supervised learning is a highly effective and level-efficient alternative for diabetic foot ulcer data classification. Our SSL model achieved 95% accuracy, proving that scalable solutions for limited data scenarios are feasible. For future work, we plan to move beyond binary classification to multi-class ulcer severity grading. We also aim to scale our work with larger and more diverse datasets, incorporate explainable AI techniques like GradGap to build clinical trust, and explore hybrid semi-supervised models to further bridge the performance gap. At last, thank you for your attention. I would be happy to take any questions.
Thank you. Thank you, Purnima, for your excellent presentation. So does anyone has any question for Purnima? Please.
Okay. What happened?
No, it is not working.
It's working. What happened that other author's name is not there? We do not have also this, some mistake is there, it happens.
If that is working, then I can use that.
No, other author's name in your presentation?
I'm sorry, I didn't include their name, but I can tell.
Okay, that's fine. Well, I think session chair will look into it. So thank you.
Okay, so am I audible? Am I audible?
Yeah, please.
Okay. So I have a couple of questions. First one is, how can this self-supervised feature learning from unlabeled diabetic foot images improve classification, accuracy, and robustness, particularly in cases with limited annotated clinical data. Am I audible?
Yes.
Yeah.
Okay. Means, improve the classification accuracy and robustness in case of these, these limited annotated clinical data. How it would be helping?
Yeah, Purnima, please. You are not audible.
Unlevel diabetic. Because that would bring the robustness.
Okay. The traditional supervised learning models understanding strongly tied the quantity and quality of labeled examples. But when data is limited, this often lead to overfitting and poor generation. But in our cases, SSL uses pretext tasks, such as for Sinclair, the models learn to recognize two augmented versions of the same images as similar. Through this process, it captures invariant and discriminating visual features, such as texture, shape, and color patterns, that are useful for many downstream tasks. Even a small level data set is enough to train a simple classifier effectively because the encoder already understands the underlying structure of the data. And I think this enough to lead to better performance in low-level settings and higher robustness to noise or variation.
Okay. Okay. So the second question is which self-supervised pretext tasks most effectively capture clinically relevant ulcer characteristics, and how do they impact downstream classification performance across diverse patient populations? I mean, self-supervised pretext tasks, for example, contrastive learning, masked image reconstruction, patch level prediction, or something like that. So, how do they impact this downstream classification performance across diverse patient populations?
I'm sorry, I couldn't hear properly. Can you please repeat?
Okay, so I repeat, which self-supervised pretext tasks most effectively capture clinically relevant ulcer characteristics, and how do they impact downstream classification performance across diverse patient populations? Means I'm talking about this, pretext task means contrastive learning, masked image reconstruction, like that. You are having that, and how that would impact this classification performance. This question is not clear, huh? Question is not clear?
Actually, I'm not grasping the question entirely. I guess you are saying the which pretext task affecting the.
Yes. So how do they impact? Okay, so fine. If you have not, addressed this one, so fine. It was a query. So fine.
It's fine. Thank you.
It's fine.
Yes, Purnima. Yeah, thanks. Thank you for your answers and presentation. Just as you mentioned that your self-supervised learning, it will be the accuracy is like 94-95%, but you didn't consider the AI thing as well. As you said that it's a huge data set and other things. So now is the time of AI, and AI will bring many more machine learning things. So I mean, how many year or months you can defend these things? I mean, if the AI is coming so rapidly, so how you then justify that you didn't use AI things, or how you gonna integrate the upcoming AI things in your project? Any thought or any idea about it, Purnima?
Actually, we want to use AI in our future work. As I explained in my future work, there's a explainable AI, and I want to use GradCam, and also to use explainable AI, which is a shape line, which can predict what features actually validate our predictions. And we will work in our future work for this.
All right. Thank you. Thanks, Purnima. Thanks for your presentation.
Thank you so much.
Now, I would like to invite the conference ID 2025345, titled as TriFuse DR, Adaptive Multi-Backbone Fusion with Ordinal Consistency for Diabetic Retinopathy Grading by MD Rakibul Hassan, M. Shamim Kaisar, MD Abu Yusuf. Please proceed.
Assalamu alaikum, and thank you for giving me the floor. Am I audible?
Yes, you are.
Again, thank you for giving me the floor. I'm Mohammad Rakibul Hassan, along with my co-authors Mohammad Shamim Kaisar and Mohammad Abu Yusuf from IIT Jahangirnagar University, Bangladesh, and my paper ID 2025345. We present TriFuse DR, an adaptive multi-backbone fusion with ordinal consistency for diabetic retinopathy grading. We'll talk about our presentation. Okay. So we'll first talk about the introduction, the background, the related works that have already been done, our proposed method, the experiment we have conducted, and the results, the limitation and future work. First, the question is, what is diabetic retinopathy? Diabetic retinopathy is a diabetes-related eye disease caused by the damage to the tiny blood vessels in the retina. Over the time, uncontrolled blood sugar levels due to the diabetes lead to the leakage and abnormal vessel growth, which can result in the vision loss or even permanent blindness. So, in case of diabetic retinopathy, we can take it as in 5 stages. In the first stage, when we have the normal eye, there is no tear. In case of no tear, sorry. So I'm taking a minute due to my screen issues. I'm just minimizing this. Okay. Now, sorry. Okay. So diabetic retinopathy, we can take it in 5 stages. In case of normal eye, there are no vision impact, as well as in case of mild non-proliferative diabetic retinopathy, where we have the microaneurysms in our dear eyes, there are no vision impact. In case of moderate non-proliferative deer, there are several vessel blockages that results in some mild blood. It becomes actually noticeable loss in case of widespread blockage in severe NPDR. The most dangerous is proliferative deer that has new fragile vessels and it impacts in severe loss. So is it a rare disease? No, actually, there are more than 537 million people with diabetes worldwide, and the estimated number of diabetic retinopathy in 2020 was more than 103 million. The projected number is a shocking 140 million plus in 2040. In my country, Bangladesh, as per the IDF, there are more than 13.9 million people with diabetes within the age of 20 to 79 years, and more than 1.85 million of those people have diabetic retinopathy. So what's actually our problem? The accurate diabetic retinopathy grading, it still remains challenging due to the class imbalance, the subtle interclass variations, and non-adaptive single backbone models. So main challenges in GR grading, those are like the subtle lesson differences. You can't directly differ the severe with the mild or the no NPDR, sometimes due to the variability in image qualities, as the ophthalmic technicians are not always there totally skilled. There are class imbalance in datasets, and the ordinal nature is oftenly ignored by the standard classifiers. The related works that we have studied, some of those are, they have did some good works. Some of used Bayesian enhanced DenseNet 121 and achieved a good accuracy. Some used a two-stage deep learning framework using the transfer learning effectively. Some used hybrid CNN models combining the ResNet and Inception models. Some has also used enhanced deep learning models for deer detection and outperforming the traditional ML methods. Still, some gaps are there presented. Some of these are the limited generalization of the single models. Actually, the most deer grading models, they rely on single CNN backbone that struggle to generalize across the variable quality and the heterogeneous retinal image. The adaptive fusion is oftenly ignored. Actually, existing ensemble models, they combine multiple models, the hybrid architectures, but they lack the adaptive mechanisms. And the ordinal relationship is rarely used. In many classification models, they treat the deer grades as only the categorical rather than their ordinal nature. So actually, the objective that we have found was to develop an adaptive multi-backbone framework to design our tri-phase deer integrating three models. EfficientNet B4 actually gives a trade-off of efficiency with its 90 million parameters size. The ResNet 152 V2 is a bit heavier than those other, but actually the skip connection give us good features, and the DenseNet 201 with 20 million parameters. We have also incorporated the ordinal aware learning. We have combined the categorical and ordinal prediction heads to our model, and we had to enhance clinical robustness and interpretability to evaluate our model for accuracy, ordinal consistency, and real-world applicability. So the key contributions that we have: first, the adaptive multi-backbone that we had in our objective, we have integrated those three pre-trained models using gating network that learns attention-based weight for the feature fusion. We have optimized dual head prediction, the classification head and the ordinal head. We have also done the comprehensive evaluation that generates an outstanding training and validation accuracy on Aptos 2019 blindness detection dataset, outperforming the other strong baselines. So what was our proposed workflow? Our proposed workflow that we have collected the Aptos 2019 dataset and make a balanced diabetic retinopathy dataset. We have done the pre-processing first for the ordinal head. As it's not present, we had to make the ordinal vector. Then we had to resize, normalize, used Clahi enhancement with augmentation. We have modeled the diffuse deer, trained and validated it, and then we have done the classification report for evaluation and metrics. The dataset, as I have mentioned, we have used Aptos 2019 dataset that actually had 3,662 fundus images, but the class imbalance was a main issue. We have mitigated the issue with augmentation, and we have also used inverse frequency class weighting to ensure the balanced and stable training. For our pre-processing stage, we have cropped our images to retinal region and resized it perfect for training. We have normalized its value to 0 to 1, applied the contrast limited adaptive histogram equalization Clahi to enhance the local contrast and the vessel visibility of the fundus images. We have used augmentation to increase the data variability, and we have encoded levels into ordinal vectors. Like if a fundus image that has like grade 3, then it will be transformed into a vector 1110 representing the grade it had, the number 3. In case of 0, it would be 0000, and for the grade 4, it would be 1111 to preserve the disease severity order. This order is often ignored in many of our works. So the structure that we had to use was the tri-phase DRE architecture. The input image was taken, that was pre-processed, and it has gone to the three backbone networks. From there, we had the projection head. We have extract and concatenated the head's features, and using a gated network with an weight that uses adaptive weights, and the summation of all the weights is sum to 1. We adaptively use the weights and then take these weights further for our addition and concatenation block. In the AC block, it squeezes and equalizes the features. Then in our shared dense network, it uses softmax and sigmoid for a different classification. The classification levels from 0 to 4 and the ordinal levels from 0 to 3. This gives us the classification and ordinal losses differently. The classification loss that we have seen, it steadily decrease over the epochs, indicating effective learning and strong feature extraction across the 5 DRE classes. And the ordinal loss that has reduced the consistently showing the model's improved understanding of the severity order and minimizing the rank inconsistencies. We then combine the classification loss and ordinal loss to get our total loss, and along with these three losses, we also get the classification accuracy. The confusion matrix is presented here. The confusion matrix shows us, if we see, in case of like grade 3 that we have mentioned before, the grade 3 is, if misclassified, it has good accuracy, though if it is misclassified, it doesn't normally results in an far different NPDR. Like it was, grade 3 was the severe NPDR. It doesn't result in the mild NPDR. So it has the lesser chances of faulty trias. The classification report is also presented, that has achieved 97.3% accuracy and a high F1 score in both mild and severe stages that demonstrate the strong generalization and the grading consistency. We have also compared with other works, and our model, due to the ordinal consistency, it actually performs better more than the state-of-the-art models. We have also did a evaluation study to show that our models getting network, AC block, or the ordinal head is actually impactful. And when we mitigate them, or when we try to train the model without this network, the accuracy actually drops. So have we achieved our objectives? Yes. The adaptive multi-backbone fusion, the tri-FuseDR, it effectively integrates those three models with gated fusion and AC blocks. The ordinal our dual head design, it combines the categorical classification with ordinal regression and reduces the misclassification, while the component effectiveness is also, we have showed in the evaluation studies. So our work, it still has some limitations. The model has not yet undergone external or cross dataset validation. The multi-backbone architecture increases the computational load actually. The current version, it still lacks the explainability analysis like GradCam. So in our future work, we plan to perform the cross dataset validation to demonstrate the robustness. We aim to optimize the model efficiency through pruning and knowledge distillation, and we will surely integrate the explainable mechanism like GradCam or attention maps to build clinical trust and transparency. So our future extensions, it target scalable real-world screening application, reinforcing the model's practical and clinical relevance. So thank you. These are some of my references that I have used in this presentation, and I'm open to question. Thank you again for giving me the floor.
Thank you very much, Rakibul Hassan, presentation. So yeah, now anybody has any question for Rakibul Hassan?
Am I audible? Can you hear me?
Yeah, now we can hear you. Your voice is a little bit breaking, so it's really hard sometimes to understand.
Yeah, after this. Yes. 2 minutes. Finish then. Okay, please proceed. Just 2 minutes. I want to finish it. Then we go. Okay. Yeah. Okay. 2 minutes. Yeah.
Yes, sir. I'm
Please.
waiting for your question.
Question, please.
Okay. So you are able to hear me, huh?
Yes.
Okay.
Yes, sir.
So can we integrate, the 3 layers here instead of 1 layer? If you have 3 layers, would that improve? This, say, we have this integrating the complementary, say, backbones in tri-FuseDR. How will it lead to more robust retinal feature extraction compared to single network approaches?
Yes, sir. Definitely a very good question. So actually, when we use the efficient net or the dense net or rest net, for a specific image, we're not sure if the efficient net will perform better or the dense net. Like the efficient net will get the better result in case of an image, and the dense net might get a better texture architecture texture for another image. So we have actually used the adaptive weight that is used for specific images, and it takes the images weight or the model features which has actually got the better results, and an weight is assigned. This weight with that feature is combined, and the better prediction that model has done for that specific image is actually got more favorable priority in the model. And in it actually does better than the single backbone models.
Okay, thank you.
Hello, session chair.
All right. So yeah, Rakibul, did you mention that what source of your data or data source did you mention in your research?
Yes, sir. It was ATOS 2019 blindness detection dataset.
It's from 2019, right?
Yes, sir.
Yeah, but I have found that your references are very current. Most of the references are like 2024, 2005. Yeah,
Sorry, sir.
most of the references.
I didn't mention it in the presentation reference, but it's actually mentioned in the paper.
Yeah. No, all good. Oh, thank you. Thank you, Rakibul. I don't have any other question. Thank you very much.
Thank you, sir.
Thank you, Professor Wahiduজ্জামান. There is another paper waiting from yesterday. He cannot present. He will be here, Aminul Sarkar. But we need a break due to some constraint for 5 minutes. You keep in session. We just changing the room due to some other reasons. So Zoom will be open just 5 minutes. Within 5 minutes, we will be in other room. But this session in Zoom, everything is here. Just our physical location we are changing due to.
Okay, but we will be here. We will be here, but physical location will be changing.
Yes.
So 5 minutes
Just,
break.
yeah. 5 minutes. I will be back. We will be back. Okay.
Okay, no problem.
Thank you. Sorry, interruption.